speaker for this afternoon's session, Tamar Ziegler. She's a pure product of the Hebrew University, having done all her bachelor's, master's, and PhD there, and she currently teaches at the Hebrew University and at Technion in Haifa. Her work has made fundamental contributions to using methods of ergodic theory in additive combinatorics. She's received many distinctions for her work, including notably the Erdős Prize in 2011. Great pleasure to welcome Tamar. Her title is Linear Equations in Primes and Dynamics of Nil Manifolds.
Does this work? Okay. So let me first start by thanking the organizing committee of the number theory session and the dynamics session for inviting me. It's a great honor to be here. Okay, so I will try to describe in this talk a kind of a mysterious connection between trying to solve linear equations and subsets, or in this case in primes, and dynamics of nil manifolds. So here's the setting. So let P denote the set of primes. Then suppose our initial settings, we're given a system of k affine linear integer forms in n variables, so psi 1 through psi k, and we want to ask this following question: can we make them simultaneously prime? And if we can answer that, then how often can we do that? So the main theorem I want to describe was proved in a series of papers by Green and Tao, and a final one by Green, Tao, and myself. And so we proved the following. So the same setting, so we start with a system of k affine linear forms of n variables, and we make this extra assumption. We assume that no two forms are affinely dependent. So x and x plus 2, unfortunately, are a bad example for that, because these two are affinely dependent. But any other system that is not hiding a kind of twin prime problem inside, so for example, if I look at a 4-term progression, so think of D here as a variable, or we can add constants, and or any system that is not hiding inside it some twin prime problem, this theorem will be applicable for it. And what we can prove is a local to global principle for these. So psi I k are all prime, are simultaneously prime infinitely often, if and only if there are no local obstructions. And furthermore, we can actually calculate the asymptotic number of solutions to the system of affine linear forms. So here's just an example. This is the example that was given in Ben Green's talk yesterday. So suppose you want to calculate the asymptotic number of 100-term arithmetic progressions of primes with the difference that is 100 factorial times a prime. So Ben mentioned that if you just wanted it to be a prime, then there are local obstructions, but if you insert this factor of 100 factorial, then there are no local obstructions, and you can actually calculate the asymptotic number of solutions. Right, so here's my goal, is to try to make an attempt of describing some results in ergodic theory and arithmetic combinatorics that motivate this theorem. Okay, so my combinatorial starting point is a really beautiful theorem of Semredi, a 40-year-old theorem. Stating the following: so suppose you have a subset E of the integers of positive density, then, so positive density just means that E takes a large portion of large intervals, or some substantial portion of large intervals. Then E contains arbitrarily long arithmetic progressions. And you can think of it as that if you take a sufficiently large subset of the integers, then it retains some of the structure of the integers. So an arithmetic progression is just a dilated and an inflated piece of an interval, or interval in N. So I want to start by describing the first non-trivial case of this theorem, known as Roth's theorem, so it's an earlier theorem. So it's non-trivial when you're looking for two-term progressions are really not interesting, but 3-term progressions are already interesting. So let E be a set of positive density in the integers, and we want to show that E contains 3-term progressions, and I want to describe to you the Roth's proof of this theorem. So how does it work? Here's the idea of the proof. Suppose you have a subset of a progression. So E is a subset of a progression. The progression is of length n. So maybe your starting point would be that you would be starting with the initial interval 1n, but you want to do some iterative process, so we'll describe this as something inside a progression. So suppose you have a subset of a progression, and the progression is of length n, and your subset is of size delta times n. Delta is some positive constant. And we want to show that E contains 3-term progressions, so here's the idea of the proof would be, well, okay, so we want to find x plus d, and x plus 2d all in E. So what is the procedure? Then procedure is the following. So either your set E has lots of progressions, or the number of progressions that is roughly what you would expect to find in a random set of the same density. So suppose you had a random set of density delta, so you would sort of flip a coin of delta probability for each element, whether it's inside the set or not, then you would expect to find delta cubed n squared progressions inside the set. So either you have the number of progressions you have is as in a random set, or roughly the same as in a random set, or your set has an increased density, so it has larger density in some sub-progression, sufficiently large sub-progression. So you sort of zoom in on a sub-progression, and inside this zoomed-in sub-progression, your set has larger density. And if you iterate this, now you iterate this process, so C is an increasing function of delta, and if you iterate this process, then after finitely many steps, you reach a subset of a progression of full density. But if your progression is at the very end, after your iteration process is of length that is greater than 3, then you've located a 3-term progression. Okay, so this is the idea, again, is either you have lots of progressions and like in a random set, and if you don't, then you can zoom in on a sub-progression sufficiently long, so say of size n to the third. Okay, so think of n as being very large, and then you iterate this, you find so you can find your progression after finitely many steps. And of course, the key difficulty is in this second step here. So how do you interpret this fact that you don't have this randomness? How do you translate that into increased density in a subprogression? And the idea here is to use discrete Fourier analysis. And the point is to show that if your set E doesn't have its number of progressions is not like in a random set, then it has a non-trivial large Fourier coefficient. So over here, this minus delta you have just normalized. So this function 1e minus delta is the normalized function. It has interval 0 or sum 0. And we have a correlation with an exponential, this non-trivial Fourier coefficient. So, okay. So this is Roth's theorem, and I will return to Semerati's theorem later. I want to describe to you the ergodic theoretic approach to this theorem, and try to kind of present it in a way that is similar in idea to the proof of Roth's theorem. Okay. So the ergodic theoretic approach was initiated by Furstenberg. So Furstenberg first observed that you can translate questions of finding subsets, nice patterns in subsets of positive density in the integers. You can translate that into a question about finding nice return times to sets of positive measure inside a measure-preserving system. So this is known today as the Furstenberg correspondence principle, and it says the following. So suppose you have a subset of positive density of the integers, and then you can associate to the subset a probability space, so x b mu, a measure-preserving transformation T, so from x to x, a distinguished set A, some special set with positive measure, such that the following happens. So you think of this big space X, and you have the set A inside, and what this thing over here is measuring is the return times to the set A. So you return to the set A in this nice arithmetic, if you can find a k and n, so you fix k. K is the length of the progression and is fixed for the rest of the world, or rest of the time, at least for today. And if you can find an n so that the measure of A, the intersection of A with its return times in this nice progression, n to n up to kn, is greater than 0, then actually you can locate a progression of length k inside, actually this is k plus 1. So a progression of length k plus 1 in your original set. So once you've done that, then you have a completely new problem. Now you can forget about your original set in the integers. You have this probability measure-preserving system, so x being mu t, so t is a measure-preserving transformation, and some arbitrary set A that you know nothing about, but you only know that it has positive measure, and your task is to find an n so that this intersection is the intersection of A with t minus na and so on is positive. Right, and indeed, this is what Furstenberg proves. So this is the Furstenberg multiple recurrence theorem. He proves that not only can you find one, but actually you can find lots of those, and the limit of the average of the measures of these intersections is greater than 0. Now, of course, you could argue that, well, this theorem is a difficult theorem to prove, and you could argue that, you know, how is your life better? You start with a subset of positive density, arbitrary subset of positive density in the integers, and you replace it with an arbitrary subset of positive measure inside a measure-preserving system. So it doesn't seem like you're much better off. But the point is that you can try to use the structure theorems for measure-preserving systems. And the idea is to study, so you try to study the measure-preserving system X by morphisms to simpler measure-preserving systems. So let me describe to you what is Furstenberg's proof of Roth's theorem. So here is the same theorem. So this is this expression over here. This is if I find just one n for which this is positive, then I found a 3-term progression. So this is an average I might be interested in. If the average is positive, then I'm very happy. So we want to evaluate this. And here's the thing that happens. Either these sets A, t to the minus na and t to the minus 2na become independent as n approaches infinity. So maybe in this average sense, but become, so either they become independent, and then this limit over here is like mu of a cubed. So either I have this kind of independent or randomness as n approaches infinity, or there is a non-trivial eigenfunction. If this doesn't happen, our system has a non-trivial eigenfunction, and from a non-trivial eigenfunction, one can construct a morphism onto a nice algebraic system. So here's how it's done. So suppose you have a non-trivial eigenfunction psi. You can, if the system, you make this extra assumption that the system is ergodic, and I won't get into that, but then you can normalize these eigenfunctions. So you can assume that it takes values in the unit circle. And if you have one of these functions, then you automatically get a morphism onto a circle rotation system by just using this psi. So I have this map x, a t from x to x, and this map psi to S1, and this diagram commutes. So if I translate by t on this system on top over here, then downstairs in the circle system, this is just rotation by the group element lambda. It's just multiplication by lambda. So you can actually collect all of these. So if you assume the regularity conditions on your phase space on your measure space X, then you can collect all these eigenfunctions. So you have only countably many of them normalized, and you get a map from X to the product of S1s, so you send X to these psi1x, psi2x, and so on. And in this system down here, you have rotation by the element lambda1, lambda2, and so on. And you can look at the image of this map. So this will denote this image Z of X. And this Z of X is what we call a Kronecker system. So what is a Kronecker system? So the phase space Z is a compact abelian group. The measure is the Haar measure invariant under group rotation. And your transformation is just rotation by group elements. So it's written in multiplicative form upstairs, but you can write it written in additive form down here. And this Kronecker factor has this universal property. It's the largest abelian factor of your system X. So if you have any other Kronecker system and a morphism from X to Y, then this would factor through this factor Z of X. So how does Furstenberg's proof of Roth theorem go then? So let pi be the morphism from X to Zx. Then this is the average we're trying to calculate. I wrote this with this function f here, but if you replace f with a characteristic function of the set A, then this average over here just calculates the measure of the intersection we're looking for. A intersect t minus na intersect t minus 2na. So if you want to calculate this average, then your original phase space might be very, very difficult to understand. You have no clue whatsoever about it, and f is just an arbitrary function, a characteristic function of a, but a is just an arbitrary set. However, if you're interested in the limiting behavior, then actually you can first project your function f onto the Kronecker factor. So you can first take your function and project it onto, push forward through this map pi, and the limiting behavior is the same as the limiting behavior of the average after you project the function f. So this is the picture you should keep in mind, is that you have a circle rotation. So you have your system X, and you have your circle rotation on the bottom. And if you're just interested in kind of this asymptotic behavior, then everything is controlled by what happens down here. So I have down at the bottom, I have z plus n alpha, z plus 2 n alpha. The map is just a rotation by alpha. So this is what the iterates look like. And on top, these x, t and x, and t2 and x are free in the fibers. There is no extra condition on them. So this is the picture you should have in mind. And once you're at this situation, your life is very good, because first, in an abelian group, it's very easy to calculate averages. You can use Fourier analysis, for example. You can use the characters of the group and actually get a limiting expression for this. And maybe I should mention that there is the key property you would be using here is that if f is projection is a positive operator. So if f is a positive function, then the projection would also be, or non-negative function, the projection would also be non-negative. So if you manage to show a theorem of this type that you were looking for before, for the system of this nice algebraic structure, for some positive function, non-negative function there, or then you obtain this theorem for the original question you were looking at. Okay. Right. So this idea motivated this definition, defined by Furstenberg and Weiss, of what they call a K characteristic factor. And it looks like a complicated, kind of a messy expression, but I do want you to sort of stare at it for a minute. And I think this is kind of a driving motivation for the rest of the developments, is this idea of characteristic factor. And so what is the idea? Suppose you're trying to calculate some complicated average on your original phase space X. So this specific average is associated with k plus 1 term progressions. But you can define this in general. You're trying to understand some average in one space, then you'd call y a factor of x k characteristic if in order to calculate this average, you can first project the functions and then calculate the average afterwards. So for example, it would be useful. X itself is a characteristic factor of itself, so that doesn't make, if you're not, the point is to try to find a really good factor down here where you have some advantage at calculating your average. So X itself is K characteristic for all K. The trivial system is one characteristic. This is the mean-ergodic theorem. So this is what happens when K equals 1, and mean-ergodic theorem to be one characteristic would tell you that you can first project the function onto the trivial factor. That's just integrating. So this is what this is the integral squared here would be what you would get from this asymptotic projection. And the key thing in Furstenberg's theorem is that the chronicle factor z of x is two characteristic. So if you want to calculate the averages associated with three-term progressions, you can first project them onto this abelian group rotation factor, this Kronecker system, and then calculate the average there. Okay, so recapping, what is Furstenberg's proof of Roth theorem? Either x is weak mixing, either we have this property that there is the asymptotic independence of the sets A, T and A, T2 and A, or there is a morphism from X to a non-trivial group rotation system. And how does Furstenberg's proof for the general similarity work? Well, there is a natural way to generalize to both notions of weak mixing and this extra structure that you get, this kind of relativize this idea. So what Furstenberg does is he constructs a universal sequence of factors denoted zkx with the following property. For in each step, we either have either the map from x to zkx is relatively weak mixing, so this would correspond to the weak mixing on top, or there is a morphism from x to a non-trivial structure, some structure, it's isometric extension of zkx. I don't want to describe exactly what this is, but this gives some structure. Either you have this relative weak mixing or some structure surfaces. Okay, so z0x, that would be the trivial system. z1x is the chronicle factor that we already met before. And the thing is that these factors, zkx, are k plus 1 characteristic. So 2, 1, yeah, so for 2 characteristic for k equals 2. So there's no way to get the indices right here. So 2 characteristic is for 3-term progressions and 1 for z1. But there, you see later, there's no way you can get the indices to work right. And the idea is that this gives sufficient structure for proving Semiramis theorem. Right. So let me mention another fact about this chronicle factor. So this chronicle factor is also what we call a universal two-characteristic factor. So it satisfies this extra property that it's the absolute best place to calculate the average, in the sense that if you have any other two-characteristic factor, so if y is any other two-characteristic factor, so y is good for calculating averages associated with 3-term progressions, then the map from x to z would factor through y. So you can think of it as kind of the most optimal place to calculate. The z of x for 3-term progression is the optimal place to calculate the average. Can't go any smaller than that. And the point is that the factors zk constructed by Furstenberg, except for this chronicle factor, except for the case k equals 1, they're not universal they're not the optimal factors for longer averages. And this brings out quite naturally the problem of classifying the k plus 1 characteristic factors as zkx. And so basically what we try to understand, so I'm reminding you of that picture, so we try to understand we have these points x, t to the nx, t to the 2nx, and so on, and we try to understand what are their obstructions, what obstructs them to sort of running away freely in your space. So let me describe to you a new obstruction that you get when you're looking at 4-term progressions. So suppose you have a 2-step mill system. So here's an example. I'll give you, so what is a 2-step mill system? So you have a nilpotent Lie group N and a gamma a lattice. So N mod gamma is compact, and you have mu is the Haar measure on Y, and your system, your dynamical system, is translation by a group element A. So here's an example that you can keep in mind. That would be the Heisenberg mill manifold. So this is you have a torus downstairs. So this is you have a circle fibers over over a two-dimensional torus. And the point is that here's what happens in this type of system. So in this y over here, you can see the Kronecker factor is what sits on the diagonal, what happens about the ones in the diagonal. So your Kronecker factor, your Kronecker system is just adding alpha beta on the, if you just ignore what happens in the third coordinate, then this is what will be what happens on the two-dimensional torus. So you have this is two-dimensional, of course, not really two-dimensional in the picture, but this is a two-dimensional torus downstairs, and the transformation is x plus n alpha. If you look at the points t to a to the a to the n, a to the 2n, a to the 3n, downstairs they look like this 4-term progression in the abelian group. And if we were just focusing on 3 of them, then we would have complete freedom on the fibers above, then no restriction on the 3 points. But if we add a 4th point, then already one of them, the 4th one is determined by the 3. So no longer, if we're looking at the 4th point, no longer is this free, these points behave freely in the fibers. And if your original system X had a factor that had a morphism onto a system that looks like that, then this is going to surface when you're trying to understand 4-term progressions. And the point is that the really beautiful theorem, and I think maybe a key step to our understanding of 4-term progressions, is the theorem of Cons, Lazine, and Furstenberg and Weiss, that this is actually all the obstructions that one has. So the only obstructions to understanding 4-term progressions come from 2-step nil systems. And in the characteristic factor language, in terms of characteristic factors, it says that the universal 3 characteristic factors are, well, there's supposed to be 2-step nil systems, but you actually have to look at inverse limits of such, so it would be 2-step pro-nil systems. It turned out that this is, was rather difficult to generalize this to general K, and this was done by Host and Kra, and another proof was given by myself. So the bottom line of it is that if you want to understand K-term progressions, then the obstructions to understanding K-term progressions in the ergodic world come from K-1 step nil manifolds, or in this case, pro-K, inverse limits of such. So what you should keep in mind is, for later, is that you have this system of factors that was described by Furstenberg. Now, they're all characteristic. They're all good enough for understanding the K-term progression theorem, or K-term progression problem. These were enough for Furstenberg to prove Semraides' theorem, but there are these optimal factors, y1 through 1k, having this extra algebraic structure coming, this algebraic nil structure, which are the optimal place for calculating these averages. And as an added benefit, you can get an asymptotic formula. So if you have a very good, thanks for that, you have the sun, kind of. So you have an asymptotic formula for, if you have a good characteristic factor with nice algebraic structure, and the dynamics on that structure are well understood, then you can get an asymptotic formula. How do you do that? You first project your function f on the K characteristic factor. This is a nil system, and on nil systems, the dynamics are very well understood. The orbit behaves very well. It's equidistributed in a sub-nil manifold. Right. So let me go back to combinatorics. So here's Gowers was trying to give a different proof. I'm not going to describe Semraides' proof. I do want to describe Gowers' proof of Semraides' theorem. So Gowers was trying to give us a proof of Semraides' theorem in the spirit of Roth's theorem. So what did he say? So suppose we start with the same context. So we have some subset E of the integers 1 through n of size delta n. And here is the beginning. So either the number of k plus 1 term progressions is roughly as we have in a random set. That was the beginning that we had in the Roth case. And the question is, or what? So what can we say if this doesn't happen? And I remind you that for the case k equals 2, we have this Fourier. We said that the function 1e has a non-trivial Fourier coefficient. So the function 1e minus delta, the normalized function, correlates with this exponential, linear exponential. And what Gowers proves is what I call a short scale obstruction to k plus 1 term progressions. And it's the following. You can partition your interval n into progressions of size n to the t for some positive t, but not, okay, so t is going to be quite small, but strictly smaller than 1 in general. So you can partition your interval into sub-progressions, and on these sub-progressions, you have a correlation with a polynomial of degree k minus 1. So for k equals 2, we have the full interval and correlation with the polynomial of degree 1. And here we would have not the full interval, but rather these intervals of size n to the t, and correlation with a polynomial of degree k minus 1 for arithmetic progressions of k, or k plus 1. Right. So, and one can use this kind of theorem to get an increased density in the same way that you do for Roth's theorem. You use the equidistribution properties of these polynomials qix. Okay, so bottom line of this is that short-scale obstructions to k-term progressions come from phase polynomials of degree k minus 2. So if I want to understand the obstructions, then they come from short scale for me is scale n to the t, when t is strictly smaller than 1. And one can do a similar procedure for any system of affine linear system of equations, satisfying that condition that I said at the beginning, that no two of them are affinely dependent. And there's a notion of complexity attached to that. And the statement of the theorem for that would be that short-scale obstructions to affine linear systems of a complexity k come from base polynomials of degree k. So an arithmetic progression of length k would have complexity k minus 2. That would work with what happens out here. But as in the Semeredi case, this is not optimal. So it's not optimal in the same sense. Well, you can find sets that have these kind of short-scale obstructions, but still have the number of configurations is still like in a random set. And we want to get the optimal structure in the same sense that we wanted to get the optimal structure for the averages in the ergodic sense that were associated with Semeredi's theorem. And so we want the optimal sort of combinatorial characteristic factor. And motivated by the role of nil systems in the study of progressions, Green and Tao conjectured that global, so global for me is full scale, so scale n obstructions to affine linear systems of complexity k come from sequences arising from k-step nil systems. So let me describe to you what this object is. So what is a nil sequence? Well, suppose you have a k-step nil manifold. So G is a k-step nilpotent group, and gamma is a lattice. So we look at a function f from G mod gamma to D to the unit disk. So D is the unit disk. It's a bounded function. And we can construct from this function a sequence, G of n, by following f through the orbit of this element A. So I have, so I'm looking at, here I chose the trivial coset. I could choose any point and follow the function f along the orbit of some point in G mod gamma. So this is a k-step nil sequence. And the theorem that we can prove is that the global obstructions to affine linear systems of complexity k come from k-step nil sequences. And not only that, but that this form is a complete set of obstructions. So it's formulated precisely, not in the kind of vague way that I did it over here. Then this would be an if and only if condition. So this would make it the universal place to calculate the averages associated with these linear systems. So what would be, in the formulation that we have for Roth and Gauer's theorem, we would say that given a system of affine linear forms of complexity k and a subset E, then either the number of configurations in E is like in a random set, or for in the Gauer's case was some local, an average over local averages on pieces, on arithmetic progressions of length n to the t. And globally we would have that the normalized function, 1e minus delta, correlates with this function g of x, which is, can't describe it in this nice form that I did, that you can with a case of Fourier analysis, but it comes from, it's a nil sequence. It's a bounded, it's a sequence that arises in the form that you have up there, and there's this bounded complexity there, notion that comes inside, that comes from, well, you see there are all kinds of hidden parameters. For example, the dimension of the manifold, the regularity conditions on the function f. So all of these are kind of hidden inside this bounded complexity and have to do with this delta that sits over here. So formalizing this theorem correctly takes quite a while, and I don't think I have time to do that. Right. So let me describe to you now how do you, so return to the original question. So we want to solve a system of linear equations, affine linear equations for primes. So here is the characteristic factor point of view on that. We start with this almost this corrected characteristic function for the primes. So we give a log x bump to the characteristic function of the primes, so that their average would be 1. And we're given a system of affine linear forms, and we want to calculate this sum. We want to estimate this sum that we have here. So whenever, yeah, okay. So how do we do that? Well, as a first step, the theorem that I described before works only for bounded functions, and this function over here is definitely not bounded as x goes to infinity. This is very large. So first of all, one can use the Green-Tau machinery from their proof about arithmetic progressions in prime to show that actually you can, in order to calculate this average, bounded functions are characteristic for this average. So you can first take this function lambda tilde and project it in some nice, there is a way to describe these things, kind of, they're not as exact in their ergodic case, but you can have an approximate progression into this combinatorial factor of bounded functions. So you want to calculate the average on top. First, you project it onto this characteristic factor of bounded functions, and then you want to calculate it there. Then, in the regime of bounded functions, you can apply the nil sequence theorem. You can apply the theorem that tells you that actually you might as well take your functions lambda and lambda tilde and project them onto the factor generated by nil sequences, the appropriate combinatorial factor of nil sequences. So this is the technology of the theorem I described before by Green-Tau and myself. And lastly, Green and Tau show that actually for this specific function that we have over here, so this would not be true for like a general function, but for the specific function associated with primes, actually they're orthogonal to all nil sequences except for very special ones, the periodic nil sequences with bounded period. So this is, I will virtually orthogonal to nil sequences. So they would be orthogonal to general nil sequences, except for those periodic nil sequences and with bounded period. From there, this is where the asymptotics, the C from the asymptotics comes from. Right, so yeah, I think I'll finish here.
Are there any questions or comments for the speaker? Yeah. If not, I'd like to thank the speaker again for her lecture and give her this closes the